James Webb is overturning almost everything in cosmology that has been accepted as true for the past century. A new ultra-deep image confirms that we have made mistakes in astronomy. The telescope that was supposed to reveal the first stars of the universe is instead destroying the prior worldview and may usher in a new science. Not all researchers are scared by the new information. Many scientists welcome the advancements because it has long been evident that something was amiss with our previous hypotheses. The inconsistencies in measuring the universe's expanding pace should have woken academics up years ago. Instead of properly reading the signals, they stuck to outdated notions. The cosmic microwave background radiation (CMBR) is thought to be the oldest in the universe. The CMBR was formed approximately 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for electrons and protons to form stable hydrogen atoms. Researchers refer to this transformation as reionization, and it made the universe permeable to light. The CMBR was discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were developing a new type of antenna. They observed a steady noise coming from all directions in the sky. This discovery was long regarded as one of the most compelling pieces of evidence supporting the Big Bang theory. Penzias and Wilson shared the Nobel Prize and made history in astrophysics. The CMB most likely provides a glimpse of the young universe. Tiny temperature changes provide significant information about the circumstances in the universe shortly after the Big Bang. Scientists used the CMB to measure the universe's expansion rate, among other things. Edwin Hubble, an astronomer, had already made this computation in the late 1920s. Hubble discovered that distant galaxies move away from us in all directions with a speed proportional to their distance. Today we refer to these measurements as the Hubble rule or the Hubble constant. Of course, Hubble did not yet have the advanced measurement techniques that were employed decades later when the CMB was discovered. Researchers recalculated the rate, and the new figure was substantially lower than Hubble's original estimate. Later scientists recalculated the rate using Type Ia supernovae as standard candles. Astronomers had access to such stable light that it could be utilized as a dependable measuring point. The discrepancy in determining the universe's expansion rate has existed since the 1990s. Since then, researchers have known, or rather suspected, that something was wrong with the assessment of the CMBR, the measuring methods, or the concept of cosmic expansion. The S8 tension, or Hubble tension, refers to the difference between the various measured values of the universe's expansion rate. This has far-reaching repercussions beyond a simple measurement difference. The many discoveries reveal profound insights into how we have previously understood the universe. For a long time, scientists were at a loss. Since its inception, the James Webb Space Telescope has provided scientists with some unexpected results which may now shed light on the conundrum of the universe's expansion rate. Galaxies so old and mature that their origin must have occurred before the Big Bang are completely incompatible with traditional science and astrophysics. There is no longer talk of mere measurement inconsistencies. Instead, academics are discussing the most serious problem in contemporary astronomy. Not only could the universe's expansion pace be erroneous, but the entire concept of expansion, or even the Big Bang, is being tested. Webb's photos reveal evidence of a universe vastly different from what we have long believed. The tension served as a first warning, and all researchers who continue to believe in outdated theories now face a challenge: do we actually know nothing about the universe? Many scientists are now standing on the rubble of their life's work, staring into space in despair, unable to comprehend what they are seeing. Given the current scientific dilemma, we must ask ourselves, what do we truly know about the universe? To address this question, we must first grasp how science works. Theoretical scientists employ a complex network of mathematical models, empirical data, and deductive reasoning to reach conclusions ranging from general to specific. Their expertise is based on a combination of observed events, experimental data, and extensive theoretical analysis. The term theory itself indicates that these are constructs and ideas, not absolute realities. We only have practical knowledge in the form of images from telescopes, sound waves, and radiation captured by radio telescopes, and the most recent data from neutrino measuring systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument at our disposal that allows us to break down the earliest light into individual frequencies and analyze it in ways that were previously impossible. Webb can show us which elements were prevalent in galaxies over 13 billion years ago, how much mass they contained, and how many stars they formed. This means the telescope can reconstruct a galaxy's shape and direction of travel. However, Webb may have flaws. In some of its photos, because of massive accretion disks, the telescope cannot determine whether we are looking at galaxies or black holes that shine as brightly as galaxies. We must confront the fact that our science has long accepted too many possible outcomes as realities while ignoring alternative explanations. Research has long been certain that it is correct. However, the most recent findings from the James Webb Telescope provide vital indications for replacing old ideas with new truths, just as has happened dozens of times in science. Scientists are currently awaiting new results. These findings are far too bizarre, and it appears impossible for many researchers to come up with fresh interpretations at the moment. The new discoveries are challenging the foundations of modern physics, which frightens many scientists. Today's physics courses are still largely based on Isaac Newton's discoveries in the 17th century. For centuries, his principles of motion and gravity served as the cornerstone for our understanding of the physical world, including the universe. Newton's rules explained the movements of objects under normal conditions and worked well on Earth. However, in space, his concepts needed to be expanded, something Albert Einstein substantially accomplished at the turn of the 20th century. Einstein's special theory of relativity, published in 1905, transformed our view of space and time. He demonstrated that space and time are interconnected and depend on the observer's motion. His general theory of relativity, published in 1915, expanded on this concept by providing mathematical evidence of gravitational phenomena based on the curvature of spacetime caused by massive objects like stars and galaxies. Despite their successes, Einstein's theories had their limits. Throughout his life, Einstein was aware that his theories would never be sufficient to describe the entire cosmos. He hoped to discover a world formula, but he did not succeed. Interestingly, no other researcher has succeeded to this day. Michio Kaku, a prominent astronomer from the United States, stated in an interview that whoever answers this challenge will undoubtedly win the Nobel Prize. Let us investigate what facts scientists may have ignored, where they may have misconstrued events, and whether our telescopes themselves might be at fault. Dark matter and dark energy are among the most likely sources of the cosmic crisis. Our current theories of the cosmos incorporate the idea that dark matter and dark energy together account for around 95% of the universe. However, neither has ever been directly observed, meaning their true existence has never been confirmed. Either they do not exist at all, and we must explain the universe's expansion and galaxy dynamics differently, or both possess properties we do not yet understand. One theory now being discussed is that the physical properties of these two dark components have evolved over time. Perhaps gravity itself behaves differently than we thought, perhaps cosmic constants fluctuate, maybe the Big Bang was never real at all. Regardless of what is ultimately discovered, the James Webb Space Telescope is pushing the boundaries of human knowledge, challenging the very foundations of cosmology, and leading us toward a new era of understanding the universe. For decades, the Big Bang theory has been the dominant explanation for the origin of the universe. It suggests that all matter and energy emerged from a single infinitely dense point roughly 13.8 billion years ago. This idea was supported by multiple lines of evidence, including However, the James Webb Space Telescope, JWST, is now revealing galaxies that should not exist under the Big Bang model. These galaxies appear. If these findings continue to be confirmed, they challenge the fundamental timeline of the universe's evolution. Some scientists are now openly questioning whether the Big Bang ever happened, or if our interpretation of early cosmic history is deeply flawed. If the Big Bang model is incorrect or incomplete, what could have happened? Instead, some alternative theories propose. The eternal universe model. Instead of a single beginning, the universe has always existed in some form, undergoing cycles of expansion and contraction. The Big Bounce theory. A previous universe collapsed and then bounced into a new expansion, creating our current cosmos. The plasma universe hypothesis. Instead of a Big Bang, the universe evolved from a highly energetic plasma state governed by electromagnetic forces rather than gravity alone. The multiverse theory. Our universe is just one of many, possibly born from quantum fluctuations or cosmic inflation. Each of these theories would require rethinking cosmic origins and developing new physics beyond what we currently understand. The mystery of dark matter and dark energy. One of the most perplexing issues in modern cosmology is the nature of dark matter and dark energy, which supposedly make up 95% of the universe but remain invisible and undetectable. Dark matter is believed to exert gravitational effects that hold galaxies together. Dark energy is thought to be responsible for the accelerated expansion of the universe. However, JWST's observations could indicate that these concepts do not fully explain cosmic structure. It is possible that Dark matter and dark energy do not exist and are simply mathematical constructs created to explain observational gaps. The force of gravity itself behaves differently on cosmic scales than previously thought. The expansion of the universe is not uniform and may be influenced by unknown cosmic forces. If dark matter and dark energy turn out to be illusions, then a new framework for physics will be needed to explain the cosmos. Einstein's general theory of relativity has been the backbone of cosmology for over a century, successfully explaining black holes' gravitational waves and cosmic expansion. However, if the JWST data contradicts expectations, it raises questions about whether our understanding of gravity is incomplete.